So this video will go over section 1.9 and 1.10. Section 1.9 on temperature. So the temperature of a substance is related to the random motion of the atoms and molecules that compose it. And this random motion is due to the average kinetic energy that the substances possess. So matter is always in constant motion. Even solids that look like they don't move, inside they are vibrating around a fixed position. Here there is a molecule moving, and so in a liquid, particles can move even more than in solids, and in gases, the particles are flying around constantly. So the hotter the object, the greater the motion, and the higher the temperature. Temperature is also a measure of how hot or cold an object is compared to another object. And so it will allow you to find out how the heat will flow from the object with a higher temperature to the object with a lower temperature. For example, if you're holding a hot coffee, the heat will flow from the hot coffee because it is at a higher temperature to warm the cup, which will warm your hand. So the heat will flow from the object with the higher temperature to your hand, which is at a lower temperature in this case. Temperature is measured using a thermometer. And so you're probably familiar with the equations that can convert temperature from degrees Celsius to degrees Fahrenheit. And for this, if you have a temperature in degrees Celsius and you want to know what it is in degrees Fahrenheit, you would use this equation that says degrees Fahrenheit are equal to 1.8 times the temperature in degrees Celsius plus 32. And if you want to do the reverse, change degrees Fahrenheit to degrees Celsius, you would use this equation that says degrees Celsius equals degrees Fahrenheit. So you would plug in your degrees Fahrenheit minus 32 over 1.8, so divided by 1.8. So these equations are given in the reference for Unit 1 in the file that is available on Canvas. So these two equations are provided there. So another temperature scale that you may not be familiar with is the Kelvin scale. It's used in science mainly. And it's used in science because it really represents what temperature is about, which is a motion. It's, you know, the higher the temperature, the higher the speed of the motion of the molecules. And in the Kelvin scale, the lowest temperature you can have is the 0 Kelvin. And 0 Kelvin is called the absolute zero and is also the coldest possible temperature. And in degrees Celsius, this is negative 273 degrees Celsius. That's the coldest temperature possible. And so the Kelvin scale is starting at 0 at that negative 273 degrees Celsius. So that's why it's the scale used in science. Whenever you have equations that are using temperature, you will need to use Kelvins because they really represent the motion. At 0 Kelvin, there is no motion. And as you go up in temperature, you have some motion and then the temperature increases. So in the Kelvin scale, there is no negative temperature. The Kelvin scale has been based on the Celsius scale, and so a change in Kelvin is the same size as a change in degrees Celsius. Notice how the Kelvin doesn't have degree symbol in front. The unit is just capital K. You would not write the degree symbol in front. So to change degrees Celsius to kelvins, you would use this equation that says kelvins are equals to degrees Celsius plus 273. And if you have kelvins and you want to get the degrees Celsius from that, you will do degrees Celsius equals kelvins minus 273. So you really see from these equations how Celsius and kelvins are related, and it's just offset by 273 for the kelvins. So again, this equation is provided in the reference for Unit 1. So here there are 3 thermometers represented, one for each temperature scale, Fahrenheit on the left, Celsius in the middle, and Kelvin on the right. And so if we compare temperatures in those 3 scales, for example, the 0 in the Kelvin is the negative 273 in Celsius, and that's negative 460 degrees Fahrenheit. That's the absolute 0. The freezing point of water will be at 0 degrees Celsius by definition. And so that's 32 degrees Fahrenheit and 273 Kelvin. Boiling point of water is 100 degrees Celsius or 373 Kelvin and 212 degrees Fahrenheit. The normal body temperature in Celsius is 37 or Kelvin's 310, and in Fahrenheit it's 98.9.6. So see how the Celsius and Kelvin scales have the same size of degrees, because when you go from 0 to 100 in the degree Celsius, you go from 273 to 373 in Kelvin. So we have 100 degrees, represent the same size in the scale. But the Fahrenheit, for the same freezing point to boiling point of water, you have 180 degrees. So a degree Fahrenheit is smaller in size than the degree Celsius or the Kelvin. So let's practice using those temperature conversion equations by doing this learning check. So please pause the video so that you practice doing this on your own before you watch the answer. So a person with hypothermia has a body temperature of 34.8 degrees Celsius. What is that temperature in degrees Fahrenheit and what is it in Kelvin? So we have degrees Celsius, 34.8 degrees Celsius, and we want that in degrees Fahrenheit. So out of the equations we have, we want to use the one that says degrees Fahrenheit equal as a function of degrees Celsius. So that will be the one that says degrees Fahrenheit are equal to 1.8 times degrees Celsius plus 32. So next you need to plug in the values. And so for degrees Celsius, you will plug in 34.8. You multiply that by 1.8, it's 62.6, and add 32. And the total is 94.6. So notice how here we keep 1 decimal. So as you can see on the bottom there, for temperature conversions, we do not follow the regular sig figs rules. Unfortunately, it's a different rule. You need to keep the same precision in the final temperature as there was in the initial temperature. And here the precision in the initial temperature was to 1 decimal place. So you want to keep the precision to 1 decimal place for your final temperature in degrees Fahrenheit. And so we need to keep 1 decimal place. So that's why here we had to keep the 0.6. And that's the same precision as the given temperature of 34.8. degrees Celsius. So now let's do the conversion from degrees Celsius to Kelvin. So here we want to use the equation that says Kelvins equals as a function of degrees Celsius. And so for this, it's going to be Kelvin equals degrees Celsius plus 273. You plug in the 34.8 degrees plus 273, and you add them, and it's 307.8 kelvins. So again, here we need to keep the precision to 1 decimal place because the given temperature was given to 1 decimal place. So you want to keep the kelvins to 1 decimal place. And kelvins typically will be in the hundreds or 200s or 300s. And so what matters is if the initial temperature was given to the ones place, you would keep it to the ones place. If it's to 1 decimal, you keep it to 1 decimal. If it's 2 decimals, you give it to 2 decimals. That's what it means by keeping the same precision. So now we will go over density and specific gravity, which are related. First, density. Density is a physical property that relates the mass of a substance to its volume. And the formula is given in your reference for Unit 1. It's reminded for you there. Density is mass over volume, or D equals M over V. Typically, the mass is given in grams, the volume is in milliliters or cubic centimeters. And so the density unit will be grams per milliliter or grams per cubic centimeters. If you have a volume and you know the density, so density will allow you to convert that volume to a mass. So if you look at the formula that says density is mass over volume, if you are multiplying both sides by volume, then you have volume times density on the left and mass over volume times volume on the right. So the volumes cancel and you're left with volume times density equals the mass. So if we look at this in units, volume will need to be expressed in milliliters if density is in grams per milliliters. So the milliliters cancel and you're left with grams. So it makes sense that you obtain the mass in grams there. To convert the mass, if you're given a mass and you want to convert that to a volume, given the density of a substance, the formula of density equals mass over volume will become, so to get mass over density equals volume, from density equals mass over volume, you will multiply both sides by volume. And so you will obtain volume times density equals mass, like we have on the left side here. And next you divide both sides by density, so that volume is by itself. And so mass over density is equal to volume. So looking at this with their units, if mass is given in grams, divided by density, if density is in grams per milliliter, so when you are dividing by density is equivalent to multiplying by the reciprocal of density or the inverse of density. So then you take the mass and multiply by the inverse of density, which is milliliters over grams. And so this way the grams cancel and you obtained a volume in milliliters. So let's go over an example of using the density as a conversion factor to see that you can use density as a conversion factor. because, for example, if the density of acetic acid is 1.05 grams per milliliter, that grams per milliliter, grams/milliliters, which means grams per milliliter, you hear the per milliliter, right? Which is a key word to tell you that you can rewrite this as an equality that says 1.05 gram of acetic acid will be equal to 1 milliliter of acetic acid. So knowing that, what is the volume of 5 grams of acetic acid? So the given amount here is not the density. Density, we just saw that it's a complex unit made of 2 units, grams and milliliters. So it's not a simple measurement and it will never be used as a given amount. The given amount here is the volume, 5 grams of acetic acid, or as the measurement with the single unit. So 5 grams of acetic acid is your given. We need to find the volume in milliliters because the density is given in grams per milliliter. So we will find the volume in milliliters. And so the density will be our conversion factor because density can be written as an equality that says 1.05 grams equals 1 milliliter, right? 1 gram per milliliter can be written like this. Out of an equality, we know that we can write 2 conversion factors. And so it can be either 1.05 grams over 1 milliliter or 1 milliliter over 1.05 grams. So we need to decide which of these 2 we will use. And for this, we look at our given amount. The given amount will be written first and then multiplied by one of these 2 conversion factors. And the one conversion factor we will choose will be the one that will allow us to cancel the grams. So that's going to be the second one. So 5 grams of acetic acid is the given amount times 1 milliliter over 1.05 grams. We know it's correct because we can cancel the grams. Remember how the 5 grams here is in the numerator, and you could draw a line below and write a 1 in the denominator. So in the calculator, you do 5 divided by 1.05, and the calculator answer is 4.761904, etc. milliliters. The unit is milliliters because grams cancelled and we're left with milliliters. So now let's look at the sig figs. The given amount was 2 sig figs because 5.0 has 2 sig figs. The 0 there is significant because we see the decimal point. The density, so the per milliliter is exact, so the 1 milliliter is exact, but the 1.05 gram is measured. But 1.05 has 3 sig figs. So between 2 and 3, the least amount is 2. So we need to keep 2 sig figs. And here, 4.7619, etc. will be rounded to 4. We keep the 7, and that's going to be 2 sig figs. What comes after the 7 is a 6, which is more than 5. So you will need to round your 7 up to an 8 and then drop everything after that. So the final answer would be 4.8 milliliters with 2 sig figs. So let's practice with this problem. Problem number 1. How many grams are in a 3.5 times 10 to the third milliliters sample of ethanol with a density of 0.789 grams per milliliter? Again, pause the video so that you work this example before watching the answer. So what is the given amount here? we have the density in grams per milliliter, and we have a number of milliliters. So as I said earlier, the given amount is always the measurement with the single unit. So density here is a complex unit of grams per milliliter, and the per milliliter here indicates that you can write this as an equality. So density will be your conversion factor. So the given is 3.5 times 10 to the third milliliters. The question is asking for how many grams do we have in that? So mass, grams are a unit of mass. Mass in grams is what we need. So to connect, we will use the density and we will write it as an equality that says 0.789 grams equals 1 milliliter. So as always, from an equality, we can write two conversion factors. And so we need to decide of the two possible conversion factors, which one we will use. For this, we need to look at the given amount. The given amount in milliliters indicates that we want to cancel milliliters with the conversion factor. And so the milliliters will have to be on the denominator. So we will use the first one. So for your setup, you start with the writing down the given amount. The given amount is in the numerator times the conversion factor written as 0.789 grams over 1 milliliter. We verify that this is written properly by cancelling units. And then in the calculator, you type 3.5 times 10 to the third times 0.789 grams. And the answer will be in grams because the grams are what's left as far as units. The calculator answer is 2761.5. So now we need to decide how many sig figs we need to keep. So the given amount here, 3.5 10 to the third milliliters, has 2 sig figs. And the density, so again, the 1 milliliter is exact. And the 0.789 grams are measured. And here in 0.789, we have 3 sig figs. So the limiting, what limits the number of sig figs is the given amount with 2 sig figs. So we need to keep 2 sig figs. So looking at the final answer and starting from the left, we count that the 2, we keep the 2, 7, we keep the 7, and that's already 2 sig figs. What comes after the 7 is a 6, which is more than 5, so you will need to round up. So the 7 will become an 8. And then we need to drop everything that comes after that. But be careful here. The value is 2761.5. We need to keep the 2 in the thousands place and the 8, because the 7 will be rounded to an 8, in the hundreds place. So we will need to add 2 zeros to show that the 2 is in the thousands place and the 8 is in the hundreds place, and then 2 zeros. Grams. So that's how we round to 2 sig figs. And make sure you do not show the decimal point, because if you were showing the decimal point, it would become 4 sig figs instead of 2. So that's the answer for this problem. Let's practice some more with the second problem. If you have 1.27 times 10 to the negative 2 kilograms of liquid ammonium with a density of 0.769 grams per milliliter, what volume will it occupy in liters? Again, pause the video before you watch the answer. So what is the given amount here? The given, again, is the measurement with the single unit. And so it's going to be the 1.27 times 10 to the negative 2 kilograms. What we need is the volume it will occupy in liters. So volume in liters. As always, the density is a conversion factor because it says it's a number of grams per milliliter. And you can rewrite this as 0.769 grams equals 1 milliliter. So here we see that our density is in grams per milliliter, but the question is asking for liters, and the given is in kilograms. So it looks like we will need to do some conversions before we can use the density as the conversion factor. So if we write a roadmap, we know we start from kilograms. From kilograms, we will need to change that to grams. And from the grams, using the density, we will change the grams to milliliters. And then we will need to finally change the milliliters into liters. So we will need 3 conversion factors, right? Because the density does not have the same units as what the question is asking and what the given amount is. So from your table of prefixes, metric prefixes, you can come up with those 2 equalities that say 1,000 grams is equal to 1 kilogram, because the value of the prefix kilo is 1,000. So 1 kilogram equals 1,000 grams. And for the milliliters, multiplying by 1,000 the quality that you get from the prefix table, you obtain the fact that 1 liter is equal to 1,000 milliliters. So now we need to find how we will write our conversion factors from these 3 equalities. So we start with kilograms. So the first conversion factor will need to change those kilograms into grams, and we need to cancel the kilograms. So the first conversion factor will have to have the kilograms on the bottom and the grams on top. So it's going to be the first conversion factor out of these 2 that are possible. Next, we need to look at that first conversion factor, which is 1,000 grams over 1 kilogram. And the next step will change those grams into milliliters. So in the next step, we want to cancel the grams. So the second conversion factor will have to have the grams on the bottom and milliliters on top. So in this case, it's going to be the second conversion factor, the one that says 1 milligram over 0.769 grams. Then the third conversion factor, to find out which one you will use, you want to look at the second conversion factor that you have, which is the 1 milliliter over 0.769 grams, and you want to cancel the milliliters. So the next conversion factors has to have the milliliters on the bottom and liters on top, so that we can cancel milliliters. So now when we put this all together, the setup will look like that. You will need to multiply the given amount first. So 1.27 times 10 to the negative 2 kilograms. Again, that's in the numerator. You could draw a line and have a 1 under. Times the first conversion factor is cancelling the kilograms with 1,000 grams on top, 1 kilogram on the bottom. Times the second conversion factor will cancel the grams, so it needs to have the 1 milliliter on top and the grams on the bottom. And the third conversion factor will cancel the milliliters by having the 1 liter on top and the 1,000 milliliters on the bottom. And we can see here that the units cancel perfectly, and that's what lets you know that this is written properly. So in the calculator, you will type 1.27 times 10 to the negative 2 times 1,000. Multiplying by the ones is not necessary. Next, you need to divide by 0.769 and divide again by 1,000. You could actually omit multiplying by 1,000 and dividing by 1,000 because, you know, these will cancel each other out. And so it really comes down to doing 1.27 times 10 to the negative 2 divided by 0.769. The calculator answer is 0.01651495. And so we need to decide what is the number of sig figs we need to keep. So the equalities or the conversion factors that come from the metric system with the prefixed unit, they are all exact numbers, the thousands and the 1 kilogram and the 1 liter. They are all exact numbers, they are not limiting. The density, the 1 milliliter is exact and the 0.769 is measured. So this is limiting to 3 sig figs. And now if we look at the given amount, it's also 3 sig figs. So we need to keep 3 sig figs in the end. So looking from the left of the final answer, the first 0 is not significant, the second one is not significant, and we start counting from the 1. 6 and 5 will be kept. And then what comes after the 5 is a 1, so we will need to round down. And so we keep the 5 and we drop everything that comes after. So the final answer will be 0.0165 liters with 3 sig figs. So a final word now on specific gravity. Specific gravity is a quantity that compares the density of a substance with the density of water at the same temperature. Because a lot of liquids are compared to water, that allows to know, you know, if they are more or less dense than water. And so specific gravity is, by definition, the density of the substance in grams per milliliter over the density of the water in grams per milliliter. And you have to do this for values at the same temperature. It is important that this is for the same temperature because density depends on temperature. You know that density will decrease as temperature increases because particles will move farther from each other and there will be less mass per unit of volume. So density will decrease as temperature go up. And it's clearly visible when you go from, you know, a gas to a liquid to a solid. Solids are the most dense, then liquids are less dense, and then gases are very light in density. Anyway, if we go back to the specific gravity here, the units of grams per milliliter in the numerator will cancel the units of grams per milliliter in the denominator. So the specific gravity of a substance does not have units, and it is equal to its density, but contains no units. We said that it's equal to its density because typically the density of water at room temperature is 1 or very close to 1 gram per milliliter. So that's why specific gravity tends to be just the density of the substance, but with no units. And that ends chapter 1.